Okay, so welcome back, especially those of you who got intrigued by this little topic that I started talking about. What I'm going to introduce next is the concept of class probability splitting rule and how it's in some situations that class probability splitting rule can help to further identify rank order match. Now, in order to understand what is meant here, let's go back to our example. And we've identified that the 9-node tree with the level of fuzziness set to 2.0 has a direct agreement on direction and rank match. So if I pick the tree here and go on the summary, if you look at the individual terminal nodes, what you see here is that now I have 5 nodes with a very high response rate, and I also have 4 nodes with very low response rate. And that's what typically happens with default CART runs. CART essentially chases after nodes as either being very rich in one class or very poor in that class. In other words, very rich in the opposite class. But that is sometimes not necessarily the best strategy to proceed. There is an alternative rule that allows CART to focus not just on the classification side of things, but also on the probability side of things. Now, we do discuss class probability trees in our training sessions and elsewhere in these videos, but this is one of those situations where you may want to experiment with that part as well. Now, in order to activate that facility, I'm going back to model setup here, and I'm using same set of settings as before. The only thing that I'm going to change is under method, instead of the default Gini improvement evaluation formula, now I'm going to switch to class probability. Now, once I switch to class probability, I build an entirely different tree sequence that now traces down probabilistic structure. And what you will discover here is that compared to the tree sequence that I had before, the new tree sequence has many more trees to look at. And that's one of the advantages of class probability trees, is that they communicate a finer structure, the kind of focus not only on classification part of problem, but also the actual probability part of the problem. So let's take this structure here, this tree sequence of trees, and post-process it in terms of train versus test consistency. Okay, so it ran fairly quickly, and as you scroll up this upper screen, it again shows 9-node tree as basically the consistent tree. But when you click on that tree, what you will discover, and especially if you compare it against the previous report, so let me organize these windows. So what you have on the left is the tree that we obtained as consistent under Gini sequence. So you have a lot of nodes with a very high lift and a lot of nodes with very low lift. In this case of a class probability tree, we have a somewhat finer transition between high lift nodes and low lift nodes. So now you're getting all of those intermediate cases, which in some applications might be of interest. Another way to see it is, again, if you go back to the actual navigator here, we've identified that it's a 9-node tree that is of interest. And when you click on the summary and the terminal nodes, you will see that this time nodes are not explicitly separated between purely ones and purely zeros, the way that we had on the previous display. And let me put those side by side also. So this was the Gini splitting rule, and this is the class probability splitting rule. And as you can see, under Gini, all of these were either pure responders or pure non-responders under class probability. Now you're getting nodes that are somewhere in between. And again, as I said, sometimes it could be an interesting additional piece of information. So let me close all of these displays and to summarize what we had. So we found a 9-node Gini splitting rule tree that's very stable. And if I look at the structure of the tree in terms of node sizes, then they are shown here. So I have 2 large nodes. One is a strongly responder, the other one is a strongly non-responder, or in this case, spam versus no spam. And there is a second tree that we obtained under class probability splitting rule. Again, it's shown to be stable. And when you look at the actual nodes, now again, you're getting a strong responder, spam node, strong non-spam node, but you also have all of the intermediate nodes based on somewhat different sets of rules that exploit the probabilistic structure of the tree and not just the overall classificational structure. And as you can see, the trees are different to some extent. Different nodes come in at the bottom of the tree. There will be very similar in the near the top splits, but then at some point they will diverge from each other, and that gives you some extra additional capability and things to look at. So to summarize, whenever you're interested in train test consistency, you should not just look at one specific tree or default tree. You should always experiment with a few more settings. Now, splitting rule is very important, in particular class probability, because it shows an entirely different kind of paradigm underneath. You may also experiment with the limits, like the limit on node size. Like if you set nodes that are too small, that is sometimes a very small node occurs very early in the tree sequence, and that essentially renders the entire tree unstable with respect to one or another stability criterion. Yeah, so in those cases, you may want to experiment with increasing the minimum allowed node size such that all of the splits are more stable and there is a more consistency between learn and test. And those are all very useful and insightful ways to understand what's going on. And again, all of these types of activities are usually when you're interested in presenting the tree structure itself or looking at the stable segments in the population. Once you move to the task of optimizing performance or finding the best way to separate things or just focus on overall misclassification rate or area under ROC curve, all of these stability issues, they kind of becoming of a lesser importance because there you're willing to trade off a little bit of instability in favor of overall better performance. But in other situations, you will be interested in tree stability, and this train versus test stability analysis report will come in very handy. And that's all I wanted to say on this specific topic.